the topic is building binary tree from traversal path, right? So you know that different types of travels is there: in order, pre-order, post-order. So if I know any two traversal, right, either pre-order or in order, I mean pre-order in order, or in order and post-order, or in order and level order. If I know the pairs of traversal, then I can able to build a binary tree. It is possible for me to build a binary tree, right? In addition to this, if you have the traversal pair, if you have the traversal pair, you should be you should have this in order traversal. Okay. So every traversal pair should consist of either pre-order or post-order. Okay, in such case, like level and in order, level order is there, that is different. Okay, now we are going to concentrate on an example also. We are going to take an example of on a single pair of single traversal pair. We are going to build a binary tree. Okay, so these are the different ways we can represent. These are the different traversal pairs, right? So if the pre-order traversal given, then the first node is the root node, that we know, right? Obviously, if a pre-order traversal is there, try to recollect the technique. Okay, how pre-order is represented. Okay, in a pre-order, okay, first we'll always represent the root node. Keep in mind the root node of a tree, and in for post-order, the last node will be the root node. So by this clue, with this kind of clue, we are going to build the tree. Okay, anyhow, we need some pre-order and post-order. Okay, once the root is identified, then all the nodes in the left subtree and right subtree of the root node can be identified using in order. Okay, so I need either in order and pre-order or in order and post-order. Okay, so if for example only we have given this type of traversal pairs, pre-order and post-order. If I give this type of traversal pair, I cannot able to find the tree properly. So that is this one. Okay, so I should have some pre-order or post-order in my traversal pair along with the in order traversal. Okay, so we are going to take an example. Construct a binary tree from a given post order and in order sequence. Okay, so they have given this is the input for you. This is the input for you. Okay, in order and post order. Right. So once the in order is given, right, and we have the post order also. What I told, always we have to check first the pre order or post order traversal. So what will I do? I'll go and check the post order. So from the post order, I come to know that last node is the root node. So now I find out that node A is the root node. So easily I'm finding, right? So I'm finding that okay, this is the root node. Okay. So anyhow, with this you cannot be only with the post order you cannot able to build the binary tree. Okay, you need some you should have some other reference also, right? So once I find this post order and look at the in order, so you check, go and check finding each and every node starting from first node. Go and check the starting from the first node whether A is matching, node A is matching with any of the element in the tree. Yes, I can find a node A in a particular place, some particular location. I can find that node A in the in order traversal. So there I stop my algorithm. Then what will I do? I consider this. I know that so this is the root node of this root node of the tree, right? A is the root node of the tree. So once again I repeat. So once a post order or pre-order given, I can easily find out the root node. Okay, I found the root node, finished. Then I'll go to in order. Directly I'll go to in order traversal. Where is the root node A? I'll keep on checking from each and every node from first to node. D, okay, it's not matching. G, it's not matching. B, it's not matching. Okay, then A, okay, it is matching. Then I stop my algorithm. Then I stop the algorithm and I fix that this is the root node. Then what I am doing, then I am dividing this uh, given input, given in order traversal as a left and right. See, DG, let me erase all the things. So A is the root node, A is the root node. One second, so some external noise, 1 second. Okay, yes. So when I find a root node A, I am dividing this in order traversal, like left subtree and right subtree. So whoever the node towards before the A, I call them it as a left subtree. Okay, whoever the node after the A is called the right subtree. Okay, so DGB is the left subtree, HEICF is the right subtree. Okay, now it's done. Fine. So that is what this steps has given, right? The same whatever I told here is given theoretically here. Okay, we are finding the node A. Okay, then this is the left subtree and right subtree is formed. Okay, then I am building a tree. Now I built a tree. A is the root node, left and right subtree. Okay, fine. Now what will I do? Now what will I do? I will take DGB now. I am going to the left part. DGB. Sorry. 1 second. So now I'll take the DGB. Okay. So from this, what can I understand? B is the root node. B is the root node. Okay. Just what I'm move to the second next slide. So next I want to find the root left and right subtrees of DGB. Right. From the post order sequence, I can come to know that from the post order sequence, the root of tree is B. Yes, post order sequence you take it. Post order sequence you take it, right? GDB. So what can I understand? So now B becomes the root node. B becomes the root node. Yes. So I found from the I found that B becomes the root node. Okay, based upon this identification, then we can find that DG or to the left. Okay, DG or left to the right. So if you look at the post order sequence, how the post order sequence is GDB, right? I'll show here also. It is GDB. It is GDB. So what I'm doing that, so I conclude B is the root node, right? And also I am looking the post order sequence. Before B, I have what? G and D. Before B, I have G and D, nothing but the left subtree. So that's what is written here, right? So before B, there are some nodes that I called as a left subtree. After B, I call that as a right subtree. But in this case, we don't have what? No right subtree. In this case, we don't have any right subtree. Okay, so I am drawing only the left subtree. Okay, dg as the left subtree of node B. Right, it's done. Up to this is clear. Okay, next what should I do? Again I'll take dg. Again I'll take dg. Okay, what should I do? I'll take the post order sequence. Okay, dg. From the post order sequence, the root of tree is what? D. Okay, and from the in order sequence dg, we can find that there is no left subtree for d and g. Yes. Okay, in the post order sequence, what I can find that what I can find d is the what root. Always you know that. So given traversal is gd, given traversal is what? Gd. So what is who is the last node? D. So since it's a post order sequence, I know that D is the root node. Once root node is known, what I am doing, I am just dividing. So the in order sequence is what? Dg, right? In order sequence is Dg. So I'm just dividing the in order sequence towards left. There's no node in the before D. So that's why there's no left child of D. But you have a node after G. A node after G. Okay, that I make it as a right subtree of D. Okay, once I make them G as a right subtree of D and it doesn't have any node at all. I mean, there is only one node in the given subtree, so that is the leaf node. That is a leaf node of, or leaf, we consider that is a leaf node or the child node of node D. Can you reply for the chat, guys? So we have left this part, right subtree. Okay, the right subtree is what? This is the traverse, HEICF. So from this we have to build the right subtree. Okay, so what I'm doing from the post order sequence, I can find that what. So let me go to the uh, question part. Okay, so uh, see here it is what? HEICF, right? Now what happens? What happens? This F is becoming what? The root node. C. Actually, according to the post order sequence, this C becomes the root node. So then I am dividing. Once I find the root node, I'll go to what? In order. Okay. From the in order, I find that I fix this is the root node. I am dividing the traversal as a left subtree and the right subtree. This is left, root, and right. Left, root, and right. So once I divide what? HA become the left subtree. Okay. Root, sorry, right is nothing but F. Okay, fine. Next, I will keep on dividing HEI, right? Once I divide HEI based upon the root node E, so I get a final tree. So this is what, how we are building a tree from the given pair of traversals. Okay, given pair of traversal, I am building a binary tree. Kidman, we are building a binary tree. Okay, so like this, there will be more problems will be there. They'll give some traversal, pair of traversals. You have to build a tree. Okay. Next, oh, this is clear. Is easy only. Next, I'll move on to the important point. Okay, implementation of binary tree. Implementation of binary tree. So implementation of binary tree. So array based implementation and pointer based implementation, right? So this slide I have shown in the last class also. This is a linked list representation. Okay, this is a linked list representation of a node in a tree, of a node in the tree. Okay, fine. Next, I want to show here the array based implementation. How we are going to store the elements of a tree or nodes of a tree in a what? In a memory. In a memory. Okay, using array implementation. Using array implementation. Keep in mind always that binary tree is binary tree can be stored in a memory. Okay, because it's very much efficient tree. It is a very efficient tree where we can store this binary tree in a memory. Okay, so what is the first point it's given? Binary tree can also be stored in arrays if the tree is a complete binary tree. Moreover, if it is a complete binary tree, we can store this binary tree in array. How we are going to store? See, for example, you take this. I will take a node. We having some 7 nodes, right? We having some 7 nodes. Let me draw here A, B, C, okay, D, D, E, F, and G. See, this tree is stored in a what? In the memory using array implementation. So what is this? A, right? B, C, D. So this is how it is stored. When I take any element in a tree, I can easily find the child elements index. For example, let us take a node B. Okay, this is what if a node has an index I. If I know the node's index, okay, I can easily find the children of this node. For example, when you take the node B, okay, I know the index of B. Okay, once I know the index of B, I can easily find out the children of B. Who are the children of B? D and E. See what this is the formula 2I plus 1. Okay, 2I is nothing. I is represents what? Index. What is the index of B? 1. What is the index of B? 1. So I am applying this. I am applying 1 to I. Okay, 2, right? So what is the value? 3. Okay, so 2I plus 1 is nothing but the left child. 2I plus 2 is the right child. So 2I plus 1 is what? Left child. Okay, who is the left child? D. So that's what, it's nothing but equal to what? 3, right? It's 3. So it means that the left child is at the index 3. So that's what it's written here. I'm drawing it again. Okay, I'm drawing it again. So if I know the index of any node in a binary tree which is implemented in array, keep in mind which is implemented in array, okay, then I can easily find the what? Find the child elements index. I can easily retrieve the value. So it is a kind of what? Searching is very easy for me. Okay, but when you take different other types of trees, you take general trees, because general tree can have what? Any node can have different types of number of trees. One node can have 3 children, one node can have 5 children, but I cannot accommodate that type of tree in the array. But it is very much complex for me. If it is the complete binary tree, it is very easy for me to retrieve the child elements easily based upon the index of the node, given node. Okay, right? For example, you take a C. Okay, C index is what? 2, right? C index is 2. So I'm applying the formula. I'm rewriting this 1 as 2. 2 to the 4 plus 1 is what? 5, right? I'm calculating the children's of index of what? F and G, because F and G are the children's of C. Okay, once I know the index of C, C is at the index 2. Okay, I can easily find out the uh, location of the left child and right child of C. So it is 5. It's nothing but where is C? It is at the index 5. Okay, F is at the index 5, and when you take G, 2I is what? I is nothing but 2, right? 2 2s are 4, 4 plus 2 6. So 6. So it is located at the right child is located at the index 6. Okay. In addition to this, we have to keep in mind the root node. Root node should start from the index 0, right? Always keep, if the root node is starting from index, for example, if you are explicitly making the root node as 1, the index is 1, then obviously this formula will not work. Okay. Ensure that the node root node A is starting at the index 0, then only this formula will work. Okay, so just I want to show here how the binary tree is represented in array. Okay, I hope this understand. Okay, and if you want to calculate the parent also, it is possible using this formula. You are applying the floor operator. Okay, you're applying the floor operator, you can easily find out the formula. Okay, yes, you just apply the same thing. If you know the child element, okay, child's index, if I know the child index, okay, then that apply the index value here. I erase it all. I will erase everything. Okay, if I know the index of child, I will apply the child's index in the I value, then I will find the parent of the particular child using in addition to that, I will apply the floor operator. Okay, you know, ceiling, floor and all, just apply. Okay. Next, we are moving to the linked representation. What is the advantage of linked representation? Okay, so array representation is good for complete binary tree only, right? It is, so keep in mind always it is uh, good for implementing the binary tree, complete binary tree, but it is wasteful on many other binary trees. Okay, you have seen different types of degenerate tree. Okay, the representation suffers from insertion and deletion of node from the middle of the tree. Okay, so these are the disadvantage of the array implementation. Whatever I'm showing here, okay, it is a disadvantage of the array based implementation. Okay, insertion deletion is not easy because as it requires the moment of potentially many nodes to reflect the changes. If I try to insert, okay, if I try to insert an element, what at particular position, what happens? We have to shift some values, right? Some more changes should happen. Then to overcome this difficulty, we represent binary tree in linked list representation. Okay, right? Next, we'll see in linked list representation how the node looks like. This is the slide where it shows how we are going to model a tree, using linked list representation. So a node is node is there. Okay, it is having 3 fields. We have seen the coding also. For each node, we are declaring 3 variables. Okay, so this is left pointer, nothing but left subtree, and this is right subtree. All node in a tree will hold the left subtree and the right subtree and the data or information. Okay, so Here why it is mentioned here, because it is a, once I know this is a leaf node, because leaf node does not have any child element, I'm making the left subtree and right subtree as null value. I'm making that as a null value. Okay, fine. So others also is there. If you are not having a null value, it means that some address is stored. It means that it is pointing to some other what, some element, some node. Okay. Okay. Next we are moving to the binary search. So binary search, it is the what the efficient type of efficient binary tree type. It's an efficient binary tree type. Okay, because in case of binary tree, you can store as it, whatever the elements comes. Okay, as like that. For example, a 8 is coming. Okay, I'm placing 8 here. 7 is coming. Say, 9 is coming. I'm placing here. Then 11 is coming. I'm placing here. Okay, then 2 is coming. I'm placing here. It goes on like this. It is in case of binary tree. I'm inserting the elements in binary tree like this. So whatever the elements comes, I will simply insert. But it is not in case of binary search tree. It follows some rules. Please recollect the binary search algorithm. Binary search, what you studied in the first year also, or in the first unit also we studied. Okay, always you will place the elements which is lesser than the particular node is towards the left side. Okay, or if the elements greater than the root node, I'll place towards the right side. That same logic only we are going to follow here. Whatever you done the binary search, okay, binary search, the same algorithm is followed here. Left subtree of a node contains only nodes with key lesser. Okay, always you can find that. See, when you take node 8, okay, node 8, you can easily find that in this left subtree of 8, left subtree of node 8, all the nodes will be lesser than the root node. Here the root node is nothing but 8. Here I'm saying, you can say here the parent node. The parent of 3 is what, 8. Okay, so left will be always will be lesser. And what is the other logic? Right subtree. Right subtree will always be greater than the node's key. Here key is nothing but the data or information. Node's key here they are telling is nothing but the data or information part of a node. The left and right subtree each must also be a binary search tree. Okay, hope you understand. So when you take any node, for example, you take 3, you take 3, you take 3. What is there? To the left of this 3 or the left subtree of 3 will be lesser than the node key 3, and you take the right subtree, always will be greater than the node 3. Okay, based upon some some logic, I can follow some alphabets. If you take alphabets, okay, I will map that alphabets to some integer value, right? I have to map, since it is 3, since it is numerical. See, the keys are numerical. Some guy is chatting. Subtree of 7. 1 second. Let me pause. So the advantages. Okay, what is the advantages? The node in a binary search tree are ordered. Yes, it is ordered. That is one of the main advantage. So once it is ordered, the time need to search an element in the tree is greatly reduced. Yes, my half of the time is reduced, right? My half of the time is reduced because I will either choose either left subtree or right subtree. For example, if we want to search element 3, we want to search element 3 in this tree. I will compare this element 3 with the root node. Once I compare, it is lesser. I find that it is a lesser. I'll directly go towards the left part of the tree. I'll directly go to the left part of the tree. I don't want to move to the right part, right? You just recollect the binary search. Uh, you have studied linear search, binary search in the first unit, right? Or in the second semester, first semester. Just recollect. Okay, same thing. My half of the time is reduced. I don't want to go to the right side. So the time is reduced here. That is one of the major advantage of this binary search tree. The average running time. Okay, so once I go to the left side or right side, now my running time is reduced. In average, I'm telling that's what order of log n, logarithmic. It takes logarithmic time. The input is 5. If input is 5, log 5. Okay, if input is log 10, log 10. That's what. Then what we have, binary search tree or widely used in dictionary. Yes, second half of your third unit, we are dealing with the dictionaries, hashing. Okay, right? There, for this type of dictionary problems, binary search tree is efficiently used. Why? Because you'll always insertion searches are very much easy in case of this. Next, binary search tree also speed up the insertion and deletion operation. Yes. Okay. If I want to insert any element in a tree, what will I do? Again, I'll compare the element, the root element. I should go to the left or right. Okay. If I go to the if it is greater than the root element, I'd go directly to the right side. I don't want to go to the left side. That's all. The same thing. If I want to delete also, the same strategy is followed. Binary search trees are considered to be efficient data structure, right? Especially when compared with sorted linear array and linked list. Okay. See, even though the linear array is sorted, right? When compared to the sorted linear array, binary search tree is best. That's what this point represents, right? And in the worst case, the binary search tree will take only what? Order of n time. It will take only the order of n time to search an element. In the worst case, I'm telling. Why? Because why this is the worst case? You will be telling that, sir, anyhow, for example, 10 elements. For example, you're having 10 elements. Sorry, 11 elements you're having. We'll take an example. Take an example. I'm taking 11 elements. So the left subtree will be having what? 5 elements. The right subtree will be having 5 elements. Okay, this one. I'm having 11 nodes in a tree. Okay, 11 nodes in a tree. Among these 11 nodes, I'm building a binary search tree. Think over that. There is a possibility of condition that there is a possible that a left subtree can have 8 elements also, right? Am I right or wrong? Left subtree can have 8 elements because depends upon the numbers, depends on the key. We are in a position to insert the 8 elements towards the left subtree and only one element in the right subtree, because we are comparing if all the elements whatever we are inserting which is lesser than the root element, obviously all the elements will go towards the left subtree only, right? It won't go to the right subtree. If all the elements you are inserting in a tree which is lesser than the root element, all elements will go towards the left subtree only. That's what we are calling as one left skewed tree. That I will call it left skewed tree. I'm just erasing all. When I will call a tree as left skewed, it means that all the elements are inserted towards the left. When I will call the right skewed, all the elements are inserted towards right, inserted towards right, I'll call that tree as a right skewed tree. Okay, see both these trees are binary search tree only, but it is not height balance. It is not balanced tree. When we have to balance the tree, why we have to balance the tree? To reduce the level. To reduce the level, a tree should be in breadth first. Okay, so for this kind of tree also, for this left skewed tree and right skewed type of tree, it takes, the worst case will take only what? Order of n time. It does not move to order of n square or order of n cube. Okay, it will not take quadratic time also. It will take only linear time. Right? I hope you understand. Nothing but we are analyzing the algorithm. Can you understand, guys? Can you give a reply? Time complexity of the binary search tree. Average case is what? Order of n. Sorry, order of log n. Average case. Worst case, order of n. Order of n. It takes this much time. This is what time complexity of the binary search tree. BST is nothing, wherever BST comes, nothing but binary search tree. Okay. Simple. Just I want to show here. I want to show whether this tree is binary tree or not. Okay. So when you take figure 1, 2, 3, it is written also here. This is not a binary tree. No means it's not a binary tree. Why? Because when you observe the tree, 22 is placed towards the left of the root node. Okay, because it is greater, it should not be placed. That's why we are saying this is not a binary search tree. Binary search tree. Whether this binary tree is a binary search tree or not. All the trees are binary tree. When I ask is binary tree or not, okay, yes, every tree is a binary tree. All the trees is a binary tree. But again, the question is whether it's a binary search tree or not. Okay, then after you find after you tell a binary search tree, then again the question, it is AVL tree or not. There's the topic is not covered in the syllabus. Most of them will be aware of this term AVL tree. AVL tree is nothing but height balanced tree. Then again the question, if it is binary search tree, it is AVL tree or not. So it keeps on, the question keeps on coming. So this is S. Okay, just observe it, and here why this is no. Why? Why it is no? Can anyone give a reply? 18. Okay, here 18 is placed at the right side of 28. Okay. So next is that we are going to create a tree. So just we are seeing the diagrammatic representation. Okay. Next we'll move on to the algorithm. Okay. This slide represents shows the creating a binary search tree. Creating binary search tree. Okay. So you will be given these elements. The question is that the input is these many elements to be inserted into a binary tree, but it has to follow the binary search tree condition. So 45 is coming, just step 1, just go through the steps, and step 2 what happens? 39 is inserted. Okay, 56, because it is greater than the root node. So always you note that the root node remains same. It's not does not changing. Whenever you into the binary search tree, the root node remains same or the parent node remains same. When you are deleting an element from the binary search tree, we have to change the parent node. That will come to the part. For creating a binary tree, no problem. For creating a binary search tree is not an issue. Just keep whatever the elements is coming, just insert by checking the logic, comparing the root element. That's all. Just I'll give 30 seconds time or 15 seconds time. Just observe how it is inserted. I'll give some 10 seconds time. hope this is understand. So just we are inserting the elements into the binary search tree. At last we are inserting 81. Not we are inserting 81. So this takes 12 steps because 12 numbers are there, 12 inputs are there. Okay. Next. So next is what? Binary search tree operation. Okay. Because binary search tree is the abstract data type. If you take any abstract data type, stack queue, right? Stack queue, tree, graph, right? You will have some operations to perform on the particular ADT. So these are the operations can be performed on the binary search tree. When you look at this, you can find the two different operation: find minimum, find max. Okay. So I want to find which is the minimum element. When I call this function find minimum function, it will fetch the element which is very much minimum in the tree. Okay. Go to this element which is the minimum element. When I call the find minimum function, it will retrieve what? Element 10. It displays the element 10 to the user. Okay. If I call find maximum, it will retrieve 81 because 81 is the, yes, sorry, 89. Here 89 is there. Okay. So 89 is there. I think so. 89 is the bigger element. Yes. So maximum function, okay, it will retrieve the maximum element in the tree. It will keeps on checking. Again, it looks the go to the root node, go to the root node 45, right? It will fetch the element. Okay, it will take this as the reference. It just holds the 45 node, and 45 node is compared with 39. It is greater or not. Okay, anyway, keep in mind find maximum will go to the right part only. It will go directly to the right subtree, right? Am I right? Find minimum will go to the left subtree because minimum element will be always towards the left part of the root node. Okay. So I'll take other display. I can display the elements in the tree, and I can perform this operation also traversal. See, all these things you have to write the coding. First we'll see the algorithm, then you can write easily the coding. This slide. Okay, so before going to the algorithm part, just a small difference between recursive and iteration, right? Recursive means what? Keep on calling the same task or same function, right? How it will be executed? For example, we take this, a program is called recursive when an entity calls itself. For iterative function or iterative type of thing, it is run under the loop. It is done under the loop. A loop is called, okay. For example, factorial function. You take the factorial function, right? If you want to find a factorial of any number, either it can be implemented using recursive fashion or iterative fashion. Okay, I can implement the what? Implement the function factorial using recursive or iterative. So if it is recursive, it will call the same function, right? It will call the same function that you know very well. Okay. If it is iterative, it will not call the same function. You'll be having some loop or either for loop or while loop. So this is done. Okay. Why I said, why I am telling here? Why I am telling here that why suddenly I have to tell about this recursive or iterative? All the operation in a tree can be executed either in recursive or iterative. So that's what I want to tell here, right? If we take this any operation, if I want to execute insert, I can implement this insert operation either in what? Either in recursive fashion or iterative fashion. it can be implemented. But in our syllabus, we are going to follow the recursive fashion. Okay, there is a disadvantage between recursive and iteration. You know about the difference between recursive and iteration. When we are to use this iterative or recursion, what is the advantage, what is the disadvantage? Just go through it. That is not our part. Okay, those are all basics. We are going to perform the recursive type of operations. Yes, this is okay, guys.